All right, let's begin section 4.3, which is a discussion of Newton's third law. We've discussed Newton's first two laws, the first law being the law of inertia, that an object in uniform motion remains in uniform motion unless acted upon by a net external force. Newton's second law says, well, if there is a net external force, this would be the acceleration, F equals ma. Now we have Newton's third law, which specifically is going to answer this question right here. We see that in the universe, there are these forces that seem to act in pairs. They seem to go together. We want to know, well, what is the relationship between these forces in terms of their magnitude and their direction? We'll touch on as well, what are some common examples of these interaction pairs? Specifically, that's going to be tension and the normal force. Let us begin. The first example that we have of an interaction pair is one in which we have a coffee cup that's sitting on a desk. Here's some picture of the idea that we have a coffee cup sitting on a desk. You could as well imagine this as a calculator, maybe the calculator that's in front of you, your textbook, sitting on a desk. Let's draw the free body diagram of this coffee cup. We see that we can represent our coffee cup with a dot. There's our object, there's our coffee cup. We have the weight of that coffee cup acting downwards towards the center of the earth. There must be some other force that's stopping it from falling through the table or through the desk, and that indeed is some force going upwards that's opposing that weight. That is the force of the desk on the cup. Force of the desk onto the cup, D onto C. Those are the two forces that are acting on the cup. We see that the net force, visually speaking, here on our free body diagram, our net force is 0, because just as strong as this force is of the desk on the cup, it's just as strong as the weight. This is what we observe, a net force of 0, because the object's not accelerating. The cup that's sitting on the desk, or the calculator that's on the desk, or the textbook, it's not accelerating, so the net force must be 0. Now there's a second free body diagram that we could analyze here, and that is the desk itself. Let's take a look at whether the force is acting on the desk. Well, again, we have the weight of the desk, which notably is probably a little greater than the weight of the coffee cup. There's the weight of the desk. We have what's stopping the desk from falling through the ground. That would be the floor. So the floor must be pushing back up on the desk. Force of the floor on the desk. But there's another force acting here, right? Isn't there something else pushing on the desk? There's the coffee cup. The coffee cup is also pushing on the desk. Force of the cup onto the desk, C onto D. Notice the interaction pair that we have here. We have the force of the desk on the cup, and we have the force of the cup on the desk. They're equal in magnitude, right? They're just as long as each other. In other words, the force that the desk pushes up on the cup to support it, that's the same that the force that the cup pushes back on the desk. So they have the same magnitude. What do you notice about their direction, though? They're in opposite directions. One of the forces is upwards, one is downwards. So we'll say they're equal in magnitude, but opposite in direction. We have a similar circumstance in, say, another example, where maybe we have, if you push against the wall, you put your hand and you push it up against the wall. So you take your hand, push it up against the wall, pushing on the wall. This is the force of your hand on the wall. All right, you push against the wall. This would be the free body diagram of the wall, right? The forces acting on the wall. Well, what about you? What about the forces on you? Well, the wall, you can feel as you push on it, it's pushing back on you, right? It's pushing back on you. This would be the force of the wall back onto you. This is also an interaction pair where we see that, well, the force of the hand on the wall has the same strength, has the same magnitude as that force of the wall onto you, or we should say the wall onto the hand, right? So maybe we should better represent this as hand, and this y should be h, right, to be consistent here. So we have what is the hand? What forces do the hand feel? Well, there are more forces here, but the one that's tied directly to this wall force is the force that the wall pushes back on the hand, and you can feel that whenever you put your hand up against the wall. They have the same magnitude, but they're opposite in direction again, right? As you push to the right, the wall pushes back on you, which must be to the left. Finally, we have a tug-of-war situation, where if we have, say, if you put your hands on a rope and you pull, what object must you be putting a force on? Well, that would be the rope. So this is a free body diagram of the rope. You're pulling, if you're on the left team, you're pulling to the left, pulling in your direction. So this would be the force of the left team onto the rope. But then we need to look at your free body diagram, or the free body diagram of the left team. As you pull on the rope, as you pull to the left, do you feel any forces acting on you? Well, suddenly you feel pulled to the right because you put your hands on the rope. You started pulling on the rope, and you started pulling on it, and you feel the rope pulling back on you. So this is the force of the rope that it puts back on the left team. Again, we see that these two forces, the force of the left team onto the rope, is the same magnitude as the force of the right team on the rope on the left team, but it's opposite in direction. All three of these examples here are examples of Newton's third law. That's what now we are going to describe, Newton's third law. A fun demonstration of Newton's third law would be if you were to place yourself up against a wall, sit in a rolly chair, and if you wanted to go from one side of the room to the other, what would you do? Well, you could push against the wall, and as you push against the wall, so say if we have, here's a wall, and here's the ground, and you're sitting in a chair. Here's a rolly chair, right? It has all the little legs. Here's the chair. Here's you in the chair. If you're trying to go this way, if that's where you want your velocity to go, well, then you could push your hand up against the wall. So you'd push on the wall here. Maybe you put a force of your hand on the wall. What happens whenever you push on the wall? Which way do you go? You go back that way. Why do you go to the right? Because the wall puts a force back on you and sends you across the room in the opposite direction. That is Newton's third law at play. Incidentally, that is how rockets work. All right, instead of having a simple single statement, or maybe a set of statements, or rather a paragraph, we'll have a set of 4 statements that together describe what we mean with Newton's third law. First, what we'll say, and what we've observed with these examples, is that forces come in pairs. We call those pairs interaction pairs, because they are forces, or they're paired up due to the interaction between objects, right? We call these interaction pairs. There's no such thing as a force that exists by itself. In our universe, that is not true. Forces always come in pairs. Our second statement here that brings up, or that puts together Newton's third law, is that we saw that the magnitude of these pairs, magnitude of each force in the pair, is the same. The magnitude of each force in this interaction pair is the same. Just as much as I push on the wall pushes back on me with that same force, same magnitude of force. That same force, however, is it's directed opposite, right? The direction of each force is opposite the other, the other force in the pair. So if one force on the wall is to the right, then the wall pushes back to the left. Direction is opposite, magnitude is the same. These forces are in pairs. And then lastly, our last point here, we'll say, is that each force acts on a different object. Each force in this pair acts on a different object. That's what we saw previously. We saw that, well, if I'm pushing on the wall, that's the force on the wall. The wall pushes back on me. That's the force on me. Notice for each of our examples, we had two free body diagrams. Our pairs of forces, one of those forces was in one free body diagram. The other force was in the other. Right? If we look back here very briefly, we had to draw two free body diagrams. Each of our pairs, here the desk on the coffee cup, here that is. The other interaction pair force is on the other object. Same circumstances here with hand on the wall and with our rope in the left team. We had to have two objects, two free body diagrams for these interaction pairs. All right, what we'll say is, therefore, we can put all of this into a mathematical equation. Don't be afraid by the word equation. It's a very simple equation. We could say that action, a force of action on something, is equal but opposite in direction to the reaction from that other object. Action equals negative reaction. More mathematically, we could say, well, there's some force. If that force is object A onto object B, the magnitude of that force is equal to the force that B puts onto A, but in the opposite direction. So Newton's third law, you could say, is one of these three things here. We could say it's this math equation here. You could say, well, it's action equals opposite reaction, or it's these four statements put together. All these four statements are shown within our equation here of force pairs. Here's our force pair, these two forces. They have the same magnitude. Magnitudes are equal. They're in the opposite direction. Here's the negative sign. And they act on different objects. That's what our subscripts tell us here. A onto B. So this is forces on B. B onto A. So these are forces on A. Two different objects. That is Newton's third law of motion. All right, so we were able, therefore, to answer this first question using Newton's third law. Before we move on to the second question of what are some common interaction pairs, I'd like you to take a look at these two problems in the textbook. Review problem page 34 on page 111 and practice problem number 28 on page 108. I'll tell you that the free body diagram for the second problem should look something like this. With this top vector longer, because the net force on this object we know is not zero, it's instead positive because the acceleration of the object is positive. But I leave that to you to take a look at on your own. Lastly, what we'll look at today are the common interaction pairs that we have in physics. There are two. We have tension and normal force. We abbreviate tension with a T and a vector symbol. we abbreviate normal force with an N, a vector symbol. When we say tension, what we mean is a force applied along a flexible medium. A flexible medium. What is an example of a flexible medium? What do we mean by that? Well, like a rope. A rope is flexible. By medium, all we mean is some physical, some chunk of matter, right? Some chunk of matter. A rope, a cable, or a rubber band. Those are all flexible mediums that transmit forces. And though these first two are the most common types of tension forces that we'll see, notice here, if I apply a force to my pen, if I apply a force to my pen from my left hand onto my right hand, if I push from my left hand onto my right hand, I can feel the force in my right hand as I pushing. Right? There's a force transmitted along this pen onto my right hand, but not along a flexible medium, so we might not call this tension, maybe. We could, technically speaking, right? This does flex a little bit. Not quite, though. Not quite as obvious as what we have here with a string. If I wanted to apply a force from my left hand onto my right hand, if I push, my right hand doesn't really feel it. But I do in the opposite way, right? If I pull with my left hand on my right hand, if I pull this way, then I apply a force onto the string. As I pull on the string, I can feel the string pulling back on me. That is why this is an example of a Newton's third law, because as I pull on the string pulls back on me, right? Just like our tug of war example. This is similar to our tug of war example. Now our normal force, this word normal, that's a mathematical word that means perpendicular. Right, perpendicular. That's why it's called the normal force. This is the force a surface applies on an object This force is perpendicular. The direction of the force is perpendicular to the surface. Perpendicular to the surface. I'll give you two examples of this. Our first example would be if we have, again, like our coffee cup resting on the table. So I'll draw a horizontal plane here. And we have our coffee cup. It's just sitting on the table. If we drew the free body diagram as we had previously, we'd say, well, there's the weight that's acting on this coffee cup. There's the weight. And then the table or the desk is holding up the coffee cup. So this is the force of the desk on the cup. We would call this force, more generally, the normal force. It's normal because it's perpendicular to the surface, and it's a force from the surface, from the desk, onto the cup. That is a normal force, a force perpendicular to the surface acting on the object. We could also have a normal force that's for an object on an angle. Say if we have some angled object, I'll give some relative horizontal. Right? So here's maybe the horizontal, and then we're on an inclined plane. We place a block on that inclined plane. We still have the weight acting on the object straight down. Here's the weight. Where is the force that the surface exerts on the block? That force is from the surface onto the block, perpendicular to the surface. Well, if here's the surface, perpendicular to it must be at 90 degrees to it. So here must be 90 degrees, shooting straight out from the surface, straight up and out, but not due north, right? It's perpendicular to the surface, so it's 90 degrees. There's our 90-degree angle. So our example here that we saw in the interaction pairs was our coffee cup example. All right, we'll begin next class with an example in Newton's third law. Thank you.